My. What do we have here? Could it be a Tektronix DPO 4034 Digital Phosphor Oscilloscope? Maybe. Oh, overexposed colors. This is yellow. This is the trace across the current viewing resistors. There's the resistors. There's the yellow probe. There's the ground. That's the current viewing resistor trace. This trace, although you can't tell now, is purple, and it's the trace across the common drains. Right. Where is it? Oh, sorry. This is the purple trace. This is the trace across the battery, not the common drains. There's the purple probe, and there's across the battery right there. And then this trace is the green trace. And the green trace, as we know, is the MOSFET common drain on the load side of the transistor. And then down here is the function generator driving trace. There's the zero. It's going all negative. 0, negative, 0, negative. Okay, here's the channel settings. Here's the time base. Here's the trigger. Here's the function generator. Unfortunately, this Clark Hess function generator is not nearly as sophisticated as my Interstate F43 that I used, but this is all I got here, and it's not as versatile, but I do have it set for all negative offset and the voltage up, and it's putting out 1,000 hertz, or 1 kilohertz. Okay, so there's that. So if I vary the function generator amplitude, you get the characteristic things, right, where the oscillations are dependent on the function generator drive. And notice where the trace is on the current viewing resistor. It's right at 0. It doesn't deviate from 0 here because I've got a negative drive pulse. But watch what happens if I push the drive pulse up to positive and turn up the amplitude. Okay. Now you see what's happened? The voltage on the current viewing resistor has gone up. So that indicates there's current flowing. There's oscillations, battery trace. So in this way, with the current up above the baseline, we know there's current flowing through the CVR. But we know that we're supposed to be using a negative offset, right? And that's where that is, just like that. Now here's an interesting thing that I discovered. The other day I showed you that the oscillations were dependent on the inductance in the series line to the battery. Well, watch this. I'll just unplug the battery. Uh-oh. Oh, is that still live? Yeah, it is still live. Battery plugged in, battery unplugged. Plugged in, unplugged. What's going on here? Oh, I have the minus lead of the oscilloscope hooked to the battery lead. Let's try unplugging that. Oh, that's what that was. Okay, so you can see that we have a nice ground loop through the test equipment. We can, depending on where the battery's hooked up, or whether the minus lead for the battery thing is hooked up, we have a situation where we can actually unhook the battery and we get very little change in the waveform. Right? Five IRF PG50 MOSFETs. This is the Q2 array. This is simulating the white pegboard and clip leads here. This is the 4 paralleled 1 ohm current viewing resistors giving a total of 0.25 ohms. This is the Q1 MOSFET, IRF PG50. And that's all the components. Well, there's this little series resistor here that I can either use or not use in the gate drive. And that's it. Oh, the load. And its little mineral oil bath and the batteries. Okay. Now tonight, I'm going to install this thing on a piece of white pegboard. Why not? And if I can figure out how to do math on this fancy oscilloscope, maybe I'll do some correct math interpretations. See up there where it says Tek Run, and if you look on the other Tektronix traces that I've published from somebody else's oscilloscope, you'll see that little Tek up there in the top left corner. Oops, sorry about the focus. Tek, see it? Blue Tek Run. Oh my goodness. My goodness. My goodness. Thanks for watching.